Welcome back to Science for Sleep, the place where we explore the deepest mysteries of the universe in a calm, immersive way that helps you relax while your mind expands. If you enjoy thoughtful science explained clearly and completely, make sure you subscribe, like this video, and leave a comment about what topic you'd like us to explore next. Tonight, we're traveling farther than any human ever has, to the very edge of the universe and possibly beyond it. Let's begin. Imagine standing at the farthest possible point in existence. Not the edge of a planet, not the edge of a galaxy, but the edge of everything. The question sounds simple: what is expanding into what? When we say the universe is expanding into what exactly? Is there something outside it? Is there an edge? Or is the idea of an outside meaningless? To answer this properly, we have to begin at the beginning. Around 13.8 billion years ago, the observable universe began in what we call the Big Bang. Contrary to the common image, this was not an explosion in space. It was the expansion of space itself. There was no empty void waiting for matter to rush into. Space and time themselves began expanding from an extremely hot, dense state. This discovery emerged in the early 20th century when astronomers observed that distant galaxies were moving away from us. In 1929, Edwin Hubble showed that the farther a galaxy is, the faster it appears to be receding. This observation became known as Hubble's law. It revealed something astonishing: the universe is not static. It is stretching. But here's the critical detail. Galaxies are not flying outward into pre-existing emptiness. Instead, the space between galaxies is expanding. Think of dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from every other dot. But the dots are not moving across the surface. The surface itself is stretching. Now here is the subtle but crucial insight. The balloon analogy has no center on the surface. Every dot sees every other dot moving away. Similarly, in our three-dimensional universe, there is no special central point of expansion. So what is it expanding into? According to modern cosmology, the universe is not expanding into anything. It is not expanding into a higher dimensional empty room. It is simply expanding. Space itself is growing in scale. This idea is rooted in Einstein's theory of general relativity, developed by Albert Einstein. In general relativity, gravity is not a force pulling objects through space. Instead, mass and energy curve spacetime itself. And spacetime can stretch, bend, and evolve. When we solve Einstein's equations for a universe filled with matter and energy, the result naturally predicts expansion. In fact, Einstein initially resisted this conclusion. He introduced a cosmological constant to force the equations to produce a static universe, because at the time scientists assumed the cosmos was eternal and unchanging. Later, after Hubble's discovery, Einstein reportedly called that adjustment his greatest blunder. But the story becomes even more fascinating. In the 1990s, two independent research teams studying distant supernovae discovered something shocking. The expansion of the universe is not slowing down. It is accelerating. Galaxies are moving away from each other faster and faster over time. The cause of this acceleration is something we call dark energy. Dark energy is not dark because it is black or shadowy. It is dark because we do not know what it is. It appears to make up about 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. Ordinary matter, the atoms that make stars, planets, and you, makes up only about 5%. Let that sink in. Everything you can see accounts for just a tiny fraction of reality. Dark energy appears to be a property of space itself. As space expands, more space exists. And if dark energy is intrinsic to space, then more space means more dark energy, which means even faster expansion. Now let's return to the central question. If space itself is expanding, is there an edge somewhere far away? The observable universe has a limit. We can only see as far as light has had time to travel since the Big Bang. That boundary is about 46 billion light-years away in every direction. This sphere is called the observable universe. But this is not the edge of all existence. It is simply the limit of what we can currently observe. Beyond that, there may be more universe, potentially infinitely more. Current evidence suggests the universe is spatially flat on large scales. Measurements from missions like NASA's Wilkinson Microwave, Anisotropy Probe and the Planck spacecraft show that the geometry of space is extremely close to flat. In a flat universe, space could extend infinitely in all directions. If space is infinite, then it does not have an edge. It simply goes on forever. But there are other possibilities. Some cosmologists suggest the universe could be finite but unbounded, like the surface of a sphere in 3 dimensions, except extended into higher dimensions. If you travel far enough in one direction, you might eventually return to your starting point, though the scale would be so enormous that it would exceed any practical measurement. Now we step into more speculative territory. There are theories suggesting our universe may be embedded in a higher dimensional space. In certain models inspired by string theory, our 3-dimensional universe could be like a membrane, often called a brane, floating in a higher dimensional structure called the bulk. In that case, when we say the universe is expanding, it could theoretically be expanding within that higher dimensional space. However, this remains purely theoretical. There is currently no direct evidence for extra-spatial dimensions beyond the 3 we experience. Another possibility is eternal inflation. Inflation is the theory that in the earliest fraction of a second after the Big Bang, the universe underwent an extremely rapid expansion. This explains why the universe appears so uniform on large scales. But some versions of inflation suggest that this rapid expansion never fully stopped. Instead, different regions of space stopped inflating at different times, forming bubble universes. Our observable universe would be just one bubble among potentially infinitely many. This leads to the multiverse hypothesis. If eternal inflation is correct, there may be countless universes beyond our observable horizon, each with different physical constants, different laws of physics, perhaps even different numbers of dimensions. In that framework, asking what our universe is expanding into becomes even more complex. It might be expanding within a larger inflating background, or it might be entirely self-contained with no meaningful outside. Now let's address some common misconceptions. First, the universe is not expanding into empty space like smoke into air. There is no pre-existing emptiness. Space itself is what is expanding. Second, there is no central point from which everything moves away. Every observer in any galaxy sees other galaxies receding. Third, galaxies are not expanding in size due to cosmic expansion. Gravity holds galaxies, solar systems, and even clusters of galaxies together. The expansion only dominates at vast intergalactic scales. And now we reach a profound implication. If expansion continues accelerating indefinitely, distant galaxies will eventually move beyond our observable horizon. Their light will never reach us again. In trillions of years, observers in our galaxy may see only the local group of galaxies, with no evidence of the wider cosmos. Future civilizations might conclude they live in an isolated, static universe, unaware of the vast cosmic history that preceded them. This scenario is sometimes called the Big Freeze. As space expands and matter spreads thinner, stars eventually burn out. Black holes slowly evaporate over unimaginable timescales. The universe grows colder and darker. But other endings are possible. If dark energy increases in strength over time, expansion could accelerate so violently that galaxies, stars, planets, and eventually atoms themselves are torn apart. This hypothetical fate is called the Big Rip. Alternatively, if dark energy were to reverse or change sign, expansion might slow and eventually reverse into a big crunch, collapsing everything back into a hot, dense state. And there are cyclic models suggesting the universe could undergo endless expansions and contractions, each Big Bang following a previous collapse. So when we ask what the universe is expanding into, the most honest scientific answer is this. Based on our current understanding, it is not expanding into anything. It is expanding in the sense that the metric that defines distances between points in spacetime is increasing. The concept of an external container may not apply. The edge of the universe may not be a wall. It may not be a boundary at all. It may simply be the limit of what we can observe. And beyond that limit, there may be more of the same, or something entirely different. As you relax and let this settle in, consider this final thought. Every direction you look into the night sky is not just looking outward in space. It is looking backward in time. The farther you see, the younger the universe appears. When we observe the cosmic microwave background, the faint afterglow of the Big Bang, we are seeing light from when the universe was only 380,000 years old. And beyond that, there is no light to see. Not because nothing existed, but because the universe was opaque before that moment. So the ultimate edge may not be spatial at all. It may be a boundary in time. And beyond that boundary, physics as we know it begins to break down. Quantum gravity, unification theories, and deeper layers of reality await discovery. The universe may not need an outside. It may be complete in itself. Endless, expanding, self-contained, and still full of unanswered questions. And that is what makes it so beautiful. If you enjoyed tonight's journey to the edge of everything, remember to subscribe to Science for Sleep like this video, and leave a comment telling me what cosmic mystery we should explore next. Now let your thoughts drift outward, past the stars, past the galaxies, past the limits of observation, into the expanding unknown, and rest. And as you rest there, imagining the expanding unknown, we move deeper into what expansion truly means at the mathematical level, because this is where the idea becomes both stranger and more elegant than most people realize. When cosmologists describe expansion, they are not talking about objects moving through space in the ordinary sense. They are describing something called the metric expansion of space. In general relativity, distances are defined by a metric, a mathematical structure that tells you how to measure separation between points. When the universe expands, what changes is the scale factor in that metric. The scale factor is a function of time. As time increases, the scale factor increases. That means the distance between two faraway, unbound galaxies grows not because they are pushing themselves apart, but because the fabric that defines their separation is stretching. Imagine drawing a grid on rubber. The grid represents space-time itself. Now slowly pull the rubber outward. The squares become larger. The coordinates remain consistent relative to the rubber, but the distances between points increase. There is no edge to the rubber in this analogy unless you artificially impose one. And in our best current cosmological models, there is no detected edge in the fabric of space. But there is something even more mind-bending. The universe can expand faster than the speed of light, and this does not violate relativity. This sounds impossible at first. Nothing can move faster than light. That rule holds locally. No object can move through space faster than light in its immediate vicinity. But space itself can expand at any rate. Two galaxies separated by enough distance can recede from each other faster than light due to expansion. This is why some regions of the universe are permanently beyond our observable reach. Their light will never reach us, not because they are moving through space too fast, but because the space between us expands too quickly for the light to ever catch up. And this leads to the concept of the cosmic event horizon. Just as a black hole has an event horizon beyond which nothing can escape, the universe has a cosmological event horizon beyond which events can never influence us. This boundary is not a wall. It is a limit imposed by expansion and the finite speed of light. As dark energy drives acceleration, more galaxies will cross this horizon. Their light will stretch, redshift, fade, and disappear. Redshift itself is another key concept. As space expands, the wavelength of light traveling through it stretches. Light from distant galaxies shifts toward the red end of the spectrum. The farther away the galaxy, the more stretched the light becomes. Eventually, visible light becomes infrared, then microwave, then radio waves, growing longer and weaker until detection becomes nearly impossible. This stretching of light is direct evidence of expansion. It is not merely motion through space. It is the expansion of space. Now let's address something that often confuses people. If the universe was once compressed into an extremely small, hot state, does that mean everything was crammed into a tiny ball floating somewhere? The answer is no. The early universe was not a ball in space. It was all of space, just extremely dense and hot everywhere. There was no outside waiting around it. There was no surrounding darkness. Time itself may have begun at that initial state. In many models, asking what came before the Big Bang is like asking what is north of the North Pole. The question may not be well defined. However, this does not mean physicists are satisfied with simply saying, "It began." There are serious attempts to understand what preceded inflation, or whether time extends further back in some deeper quantum framework. One approach comes from quantum gravity. At extremely small scales, the smooth fabric of spacetime may break down into something discrete or emergent. Some physicists believe spacetime is not fundamental at all. It may arise from more basic quantum information structures. This leads us to the holographic principle. The holographic principle suggests that the information describing a volume of space may actually be encoded on a lower dimensional boundary. In other words, our three-dimensional reality might be describable by information stored on a two-dimensional surface. This idea was inspired by black hole thermodynamics. When physicists studied black holes, they discovered that the amount of information a black hole can contain is proportional not to its volume, but to the area of its event horizon. That was shocking. If this principle applies universally, then our entire universe might be analogous to a hologram projected from some deeper boundary structure. Does that mean there is literally a wall somewhere projecting reality? Not necessarily. The holographic principle does not require a physical wall in the way science fiction often portrays. It is a statement about how information and gravity relate. Still, it invites the unsettling possibility that what we perceive as three-dimensional depth may emerge from something more fundamental. And then there are black hole cosmology models. Some researchers have proposed that our universe could exist inside a black hole that formed an apparent universe. In this model, what we perceive as the Big Bang might correspond to matter collapsing into a black hole elsewhere. Inside that black hole, spacetime would expand in a way that resembles our universe's expansion. If this idea were true, then every black hole in our universe might give birth to its own baby universe. Reality could be a branching tree of cosmic generations. Now we enter more speculative territory, the simulation hypothesis. The simulation hypothesis proposes that our universe might be a computational construct. In this view, expansion might not require an outside in physical terms. It could simply be an increase in allocated computational resources. The observable horizon might correspond to a rendering limit. Physical constants might represent programmed parameters. However, while intriguing, this idea currently lacks empirical evidence. It remains philosophical rather than testable science. It is important, especially in a channel devoted to real understanding, to distinguish between theories grounded in mathematics and observation, and those that are imaginative extrapolations. Now let's address conspiracies. Some claim that agencies hide knowledge of a literal edge of the universe. There is no evidence of this. Cosmological data is publicly available and analyzed by independent teams worldwide. Measurements from missions like the Planck satellite are scrutinized globally. There is no hidden wall detected at the edge of observable space. The edge we encounter is simply the limit imposed by light travel time. Another conspiracy suggests the universe is expanding into a pre-existing void and that this void has properties intentionally concealed. Again, no evidence supports this. All observations are consistent with expansion of spacetime itself, not motion into an external container. That said, science remains open. If evidence emerged tomorrow suggesting higher dimensional embedding or exotic topology, cosmology would adapt. The universe does not care about our expectations. Now let's think about topology more carefully. Space can be finite without edges. For example, a three-dimensional analog of a torus, like a higher dimensional donut, could allow travel in one direction to eventually loop back. In such a universe, there is no boundary to fall off. There is no edge to reach. Yet the total volume is finite. Searches for repeating patterns in the cosmic microwave background attempt to detect such topologies. So far, no conclusive evidence of a small closed topology has been found. If the universe is finite and closed, it must be far larger than the observable region. Which brings us to infinity. If space is truly infinite, then beyond our observable horizon there are infinitely many galaxies. Given infinite space and finite possible arrangements of matter, there could be regions identical to ours. Somewhere beyond the observable boundary, there could be another Earth, another version of you listening to another version of this explanation. This is not science fiction. It is a logical implication of infinite space with statistical distribution of matter. But infinity is difficult to grasp emotionally. So instead, return to something simpler. Right now, as you breathe calmly, the universe is expanding. The distance between galaxy clusters grows by tiny fractions each second. On Earth, gravity binds us so tightly that expansion has no noticeable effect. Atoms are not stretching. Solar systems are not drifting apart. But on the largest scales, the cosmic web, vast filaments of galaxies, slowly spreads outward. And the expansion rate is encoded in a value called the Hubble constant. Interestingly, there is currently tension in measurements of the Hubble constant. Different methods produce slightly different values. This discrepancy could hint at new physics, perhaps something incomplete in our understanding of dark energy or early universe dynamics. The universe may still have surprises waiting. And here we return to the original question one more time with clarity. What is expanding into what? According to our best current understanding, the universe is not expanding into anything. The expansion does not require an external dimension. Space itself is dynamic. Its geometry evolves. The idea of an outside may be a category error, applying everyday intuition to a structure that does not behave like objects within it. There may be more universe beyond what we see. There may be other universes. There may be deeper quantum structures underlying spacetime. But there is no evidence of a literal edge in the way we imagine borders. The edge is observational, not physical. And perhaps the most humbling realization is this. We may be asking the wrong question. Instead of what is it expanding into, the deeper question may be, why does spacetime exist at all and why does it evolve? That question leads to the frontier of physics, where general relativity and quantum mechanics meet. And that frontier remains unfinished, which means the story is still being written. And you are alive in the era where humanity is beginning to understand its cosmic origins. As your thoughts soften and drift outward once more, imagine the universe not as an object in something larger, but as a self-contained unfolding of geometry and energy. No walls, no edges, just expansion. Not into something, but as something. And for now, that is everything we truly know.